So today I'm starting lecture 21 on helicopter dynamics, and today I'm going to discuss boundary conditions for the rotating beam problem. I'm Dr. Ranjan Ganguly. Now in the previous lecture we looked at the elastic blade model, which you can see here, and essentially we looked at a cantilever beam, but the model when we developed it was valid for all possible boundary conditions. So this is a typical cantilever boundary condition. So this is fixed at the root and it is free at the tip. And so we assumed some forcing on this blade, and then we said there is a direction R here, there is a displacement W, and also there is a rotation. With these basic concepts behind the model, we then derived the governing equation of motion. So we first got this equation here of the derivative of the shear with respect to R, and then we saw that from strength of materials the shear S can be written as the derivative of the moment. So that led us to this equation. And then when we combine these two equations here, we take one more derivative, then we can write this partial differential equation, which essentially governs the behavior of the rotating beam. And as I mentioned before, this first term was the flexural stiffness term, the second term is the inertia term involving the mass per unit length, and the third term is the term which involves the axial tension T, which is typically a function of R. And you also have a forcing on the right hand side of the equation, which essentially causes this blade to vibrate and creates the response being W. So essentially when you solve this equation, you are solving for W R of T with this forcing in mind. Now, as I mentioned before, it's difficult to solve this equation, but we will get back to that in a later lecture. Today we are just going to see how you are going to solve this equation. So essentially, if you were to solve this equation, you would get some solution, but you would still require certain things which are known as boundary conditions. So if we look at this differential equation, this is order 4 PDE in R. So what that means is that if you look at R here, there is a fourth derivative of W with respect to R. So you are going to require 4 boundary conditions for this problem, because as we will see later, we are going to get 4 constants when we solve this equation in terms of R. So these boundary conditions essentially depend on the physics of the problem, and basically the physics of the problem in terms of the boundaries are communicated to this equation through the boundary condition. Note that the equation itself does not have any physics right here about the nature of the boundary. So let's look at each of these boundary conditions specifically. So I will look at one end at a time. So here I am looking at the pinned end. So essentially this end is pinned or simply supported. There is a pin here or a hinge. And this is known as a simply supported boundary condition or as a pinned boundary condition. Now straight away we can see from geometry that there is going to be no deflection at this point. So W is going to be 0 at this particular hinged boundary condition. And also because there is a hinge, there is going to be no moment. So the moment is going to be 0, which essentially would mean that the second derivative of displacement is going to be 0 at this particular point. So these are the two boundary conditions corresponding to the pinned or simply supported end. Now if we were to look at a fixed end, that is something like this, we can clearly see from geometry that at the fixed end W is going to be 0, so there is no deflection. We also see that if you are going to bend this beam, it's going to go something like this. So essentially at this location the slope of deflection is also going to be 0. So both these are coming out of the geometry of the problem and the physics of the problem. So this is how the fixed boundary condition communicates to your equation of motion that it is in a fixed situation. Now let's look at the free end, which is typical of the second end of typical helicopter blades or rotor blades. Now if we take this as a free end, then we clearly see that at the free end you would have a moment which would be 0, and you would have a shear force which would be 0, because if you compare it with what we had when we derived the equation of motion, we neither have a moment acting here nor we have a shear force acting here, so these two are going to be 0, which essentially would mean that if you had a uniform beam type situation, you would get the second derivative and the third derivative to be 0 at the free end, the derivatives being with respect to displacement. Next we look at the situation where you have a vertical spring. So here we have put a spring at this particular end, and the effect of this spring is that if I give this beam a displacement W, I get a force here Kw, and if we compare it to the usual nomenclature of positive shear force S, which is positive in this direction, then we see that this is going to be negative, and therefore here we have the boundary condition S is negative Kw and M is 0. So from these two equations we can derive the boundary condition for the vertical spring situation. The next case is a leaf spring, which is like a bending spring. So we attach this spring here, and the thing this spring does is it creates a moment. So we see the moment is created something like this. It's a positive moment, and therefore our boundary condition becomes M equals K theta dW by dr. So remember, dW by dr is like a slope, so it is like a theta. So essentially this K theta is multiplied by this slope, and that essentially creates the moment at this particular boundary point. The shear force is 0 in this case. So these are the boundary conditions for the typical leaf spring. So what's the practical point about these boundary conditions? Well, if you have a hingeless rotor blade, you would recognize that one end would be fixed, the second end would be free. That's common for many rotor blades. And also if you have the articulated rotor blade, one end would be pinned or simply supported and the second end would be free. So these are some of the boundary conditions we use for a rotating blade problem, rotating beam problem, and so on. Now beside boundary conditions, you would realize if you look at this equation carefully that you also have the term with respect to time. So the term involving mass involves the second derivative with respect to time, and therefore it is going to give you a solution with two constants, and to determine these constants you need to find two conditions, and these are typically known as the initial conditions for the problem. So for this beam problem, it's often the case that at t0 W and dW by dt are specified. So if these are specified at t is 0 or at some different t, then you can use these to find the constants which come in the solution because of time. So just to recapitulate, the governing differential equation for the rotating beam would give you a solution, and you would need four boundary conditions to find the constants which come from the spatial side of the equation, and you would need two boundary conditions to find the constants which come from the temporal or time side of the equations. And once you have all these boundary conditions and the initial conditions, then you can actually solve the equation in terms of all the constants, and you can get some solution which you can actually plot as a figure and use in your work. So without these initial and boundary conditions, you will only get mathematical functions, you will not be able to express these functions in any numerical manner because these are going to be dependent on these constants a, b, c, d, e, f, and so on. So I will end this video here, and in the next lecture we will start looking at ways to solve this equation. So we are not going to solve this equation. We are going to assume t is 0 and solve the non-rotating beam equation, and that is going to give us some insights into how we can go about solving the complete equation in many cases. See you then.